The second system of deductive logic that we're going to study is called natural deduction. What natural deduction allows us to do is derive the conclusion of a valid argument using rules. These rules themselves are forms of valid arguments. They're small pieces of reasoning that are themselves valid. If you remember your days of constructing geometry proofs, or you still balance your checkbook, then you have some idea of how natural deduction works. Let's get started. So, as I mentioned just a moment ago, we're going to learn how to use inference rules to derive steps in an argument. The goal is to demonstrate how it is that an argument's premises yield the conclusion. So what we'll be looking at is exclusively valid arguments. There are, after all, no ways for us to use inference rules to derive the conclusion of an invalid argument. What we want to be able to think about as we get into this chapter is that, like we did with categorical logic, we're going to look at a statement's structure in a specific way, a statement's logical structure in a specific way. For natural deduction, that means using the symbols that are enlisted in propositional logic, or also known as sentential logic. And I'll tell you what that symbolization is. But the basic idea here is that rather than taking any sentence that is true or false and translating it into standard form for a categorical proposition, we're going to use capital letters and a few other symbols to articulate what are called simple and compound statements. Our artificial language is made up of three elements. First, we have simple statements. Simple statements are those statements that do not have a connective. Now you might ask, well, what's a connective? We'll get there, but for right now, that's the easiest way to define a simple statement. We're going to symbolize a simple statement with a capital letter A through Z. Here's an example. Cheryl is a nurse. So as with our previous system of deductive logic, in natural deduction, we enlist an artificial language to help us organize statements for logical clarity. All right, another element is the compound statement. And the compound statement consists of at least one simple statement and at least one connective. Our connectives are 5 in number, but we're only going to use 3. So I'm going to present just, or I said 5, I said there are 5, we're using 3, we're using 4, sorry about that. And they are negation, conjunction, disjunction, and conditional. You'll notice a symbol next to each connective. The squiggle mark next to negation, to the right of the word negation, is called the tilde. The dot next to the conjunction is called dot. The lowercase v next to the word disjunction is called the wedge. And next to the conditional, to the right of the conditional, is a sideways U. That is called the horseshoe. Now again, just a reminder, the elements in the artificial language that we're studying or that we're using in natural deduction is meant to reveal the logical structure of ordinary language statements. And they may be hard to read at first, but they make working with really complicated statements visually much easier. And this is particularly the case when you understand what these operators are, what the connectives are, and what they do. And I mentioned that a simple statement is a statement that has no connective. You now know what a connective is. So a simple statement is a statement that cannot be further reduced without thereby losing its status as a sentence that's either true or false. So when we symbolize the statement Cheryl is a nurse, we use either S or N, And when we compound that statement, we do so by way of adding a negation if we're negating the simple statement, or we may include another simple statement and connect that to the statement about Cheryl in such a way as to generate the compound. And I'll give you some examples in just a moment. Lastly, we use parentheses when we have a compound statement that we want to treat as a unit in a larger compound statement. In addition, parentheses can be used, or alternatively, I should say, parentheses can be used to express the scope of a negation. Let me give you some examples. Recall the simple statement, Cheryl is a nurse. That's symbolized with the capital letter S. Johann is not a nurse. The simple statement is Johann is a nurse. That's symbolized with the capital letter J. There's a negation in front of the J to symbolize that the statement Johann is a nurse is negated. Cheryl is a nurse, but Johann is not involves two simple statements, S and J, along with two connectives. The dot symbolizes the conjunction, which is what the ordinary language word but expresses. And then the tilde or tilde symbolizes the negation. So S dot negation J asserts Cheryl is a nurse, and it's not the case that Johann is a nurse. Next, we have the statement, neither Cheryl nor Johann is an EMT. Now, the letters S and J were already used to designate the sentences respectively, Cheryl is a nurse, Johann is a nurse. So now when we're talking about Cheryl and Johann being EMTs, we use different capital letters to reflect each simple statement. So let's let E stand for Cheryl is an EMT, and T stand for Johann is an EMT. You'll notice that the capital letters are arbitrary designations, but they need to be used consistently in an argument so that you don't use one capital letter to mean two different simple statements. Now, notice that this statement is in terms of the least compounded part of it, asserts that either one or the other, right? So we have either Cheryl or Johann. But then the statement as a whole is negated. So we have neither one nor the other. So the symbolization involves parentheses. Why? Because as I just mentioned, the negation covers the sentence as a whole. And the sentence as a whole initially is the disjunction. So we have negation, parentheses, E, wedge, T, close parenthesis. Not either E or T. Another way you could say it is not either E nor T. Next we have another negation. Not both Rashawn and Glona are pediatric nurses. It's not the case that both. So tilde, parenthesis, R dot G, close parenthesis, not both. Lastly, we have the following. If Rashawn is a pediatric nurse, then Glona is not. What we do is translate our if-then statement with whatever comes immediately after the if clause, the word if. That clause goes on the left side of the horseshoe, and whatever comes after the word then goes on the right. Now, in terms of the work that you'll be doing for practice, you, in the textbook at least, you'll have the opportunity to work some translations, but that's not a skill that you need to develop for our work. Instead, I'm just giving you this as background so that you know what you're looking at when you see all this notation as we look at these rules that we will use to derive the steps in a proof of a valid argument. So going back to our last example, if Rashawn is a pediatric nurse, then Glona is not, we get R horseshoe tilde G. Okay, now let me give you an example of an argument that is already in propositional logic notation. In other words, capital letters for the simple statements and connectives that operate on one or more simple statements. Take a look at two versions of the same argument. The first version reads as follows: evil exists. If evil exists, God cannot be all-powerful. If evil exists, God cannot be all good. So, God is not all-powerful and he is not all good. Another way to put the argument is in less maybe religiously controversial terms. Ed is excellent. If Ed is excellent, Ed cannot be a putz. If Ed is excellent, Ed cannot be a goober. So, Ed is not a putz and Ed is not a goober. Now take a look at the three statements. Statement number 1 is a premise. That is E. Ed is excellent. Statement number 2 is also a premise, and that reads, if E, then not P. And statement 3 is a premise. That reads, if E, then not G. The premises are all lined up, one on top of the other. To the right of the last premise, behind a slash, is the conclusion. It's not the case that Ed is a putz, and it's not the case that Ed is a goober. So what we need now is to show how that conclusion, not P and not G, is derived from the three premises. Okay, so you have in the first three sentences what you saw on the previous slide. And to the right of the third sentence, you have your conclusion. So sentences 1 through 3 are the premises that were given, and the sentence not P and not G is the conclusion. Sentences 4, 5, and 6 are the steps that are involved in deriving the conclusion. Well, 6 itself is the conclusion, but 4 and 5 are involved, along with 1, 2, and 3. So think about it this way. Sentences 1, 2, and 3 are the premises. Sentence 4 is an intermediate conclusion that itself is used as a premise to get to sentence 6. 5 is an intermediate conclusion that is itself used to get to sentence 6. So all counted, sentences 1 through 5 are used to derive sentence 6. So let's take a look at sentences 1 and 2 and sentences 1 and 3. If you think back to chapter 1, you'll remember that there are some argument forms that are always valid. And when you look at sentences 1 and 2 and sentences 1 and 3, you see two versions of one valid argument form. Sentence 1 says that E is. Sentence 2 says that if E is, then P is not. That allows us, these two sentences, to infer that not P. In other words, think about it this way. If Ed is excellent, then he's not a putz. Ed is excellent. That's what sentence 1 says. So Ed is not a putz. That's what sentence 4 says. Sentence 3 says, if Ed is excellent, then he's not a goober. Sentence 1 says, That's right, Ed is excellent. So sentence 5 follows, Ed is not a goober. Lastly, if it's true that Ed is not a putz, and it's also true that Ed is not a goober, then it's true that he's both not a putz and not a goober. Here are the first 4 of 8 rules of inference that we will employ when working our way from a set of premises to the conclusion of a valid argument. Now, one of the nice things that we get in our practice on Dashboard is, as well as in the textbook, but I'm thinking specifically of Dashboard, is a way to check proofs. So when you're working on the textbook exercises, you can certainly check your answers. I can help you with those. But if you use the proof checker in Dashboard, you'll get immediate feedback. The other part of the practice that's quite nice in our textbook and in Dashboard is that you're given steps whereby you can work exercises that help you see simple steps, that is, one inference from one premise to a conclusion or 2 premises to a conclusion. And you can see those moves in the midst of otherwise kind of complicated looking symbolic statements. Then you also have the opportunity to complete constructed proofs. So you're given a proof that is constructed and you complete it by filling in the blanks. Very often you fill in the blanks for the citations, that is, which line number or numbers you use to derive a specific step, and the rule that justifies the move. So first we have the mode of affirmation or modus ponens. That rule says that when you have 2 premises, one of which is a conditional and the other of which affirms the antecedent, that is, it affirms the left side of the conditional, the consequent follows, the consequent being the right side of the conditional. Now take a look at modus tollens, or the mode of denial. Here again, any statement in the universe that's governed by a conditional, and then any statement in the universe that is a rejection of the consequent of the aforementioned conditional, is going to derive, or yield, I should say, a rejection of the left side. So let me restate this a little less verbosely. So we have, if P then Q, not Q, so not P. If antecedent, then consequent, it's not the consequent, so it's not the antecedent. In addition, you have hypothetical syllogism. This rule says that when you have 2 hypothetical or conditional claims, and one of the conditional claims consequent is the antecedent of the other conditional claim, then you can bring down or infer a conditional relationship between the antecedent and the consequent of each. So again, let me put this in what I hope is clearer terms. You have 3 elements, P, Q, and R. Notice that P is the antecedent in one claim. Q is the consequent in that claim. But Q is also the antecedent of the other claim. R is the consequent of that second claim. Q essentially transfers the relationship from P over to R. So we have the following. If P then Q, and if Q then R, it follows that P then R. Lastly, in terms of the first 4 rules, we have disjunctive syllogism. This is a process of elimination. When you assert that you have one or the other, and you reject the one, it follows that you have the other. So, if you have P or Q, and it's not the case that you have P, then you must have Q. The other version of this argument denies the Q and yields the P. So what we'll do rather is this. When we have steps in an argument that allow us to, let's say, dismantle the horseshoe, as is the case with Modus Ponens, Modus Tollens, or reorganize the horseshoe, as in the case of the hypothetical syllogism, those are the moves that we make. Similarly, if we can dismantle a disjunction by way of disjunctive syllogism, we do that. Here are the last 4 of the 8 rules that we'll learn. Now, I know that constructive dilemma looks a little bit complicated, but let's read through it and you'll see that, in fact, it's fairly straightforward. Here in the first premise, we have the following. If P then Q, and if R then S. Notice that the second premise is a disjunction, but it's the disjunction of the antecedent of each of the first and second conditional claims in the first premise. So let's look at what we've got again. If P then Q, and if R then S, and we have either P or R, then we have either Q or S. It's kind of like a possible Modus Ponens move. Remember, when we have a horseshoe and we affirm the antecedent, that is, the left side of the horseshoe, we must infer the right side. Now, P or R says we have one or the other. Maybe we have both, we're not sure. But when we have at least one or the other, that means that we have at least one or the other of the consequent of each conditional claim. The last 3 rules are pretty straightforward. Notice, by the way, that simplification and addition are single premise inferences. In other words, constructive dilemma and conjunction, along with Modus Ponens, Modus Tollens, hypothetical syllogism, and disjunctive syllogism, all involve 2 premises that yield a conclusion. Simplification and addition involves 1 premise. Let's take a look at simplification. Here you have a conjunction. A conjunction is true when and only when each of the conjuncts is true. Think about what we mean, for example, when we say both. When we say both are the case, that means that one of them and the other one must be the case. Or another way to put it is, when we say both are, we're saying that each is. So, if we have both, it means that we have one. If we have both, it means that we have the other. There are 2 versions of simplification. Addition proceeds in the following way. When we have some statement P, it follows that we have P or Q. When we have some statement P, it follows that we have Q or P. In other words, this rule follows from the truth definition of a disjunction. In order for a disjunction to be true, you need at least one of the disjunctions to be true. In other words, when we have a P disjunction Q statement, the disjunction is true when P is true, and it could also be the case that Q is true. It could be the case that P is true, Q is false. Could be the case that Q is true and P is false. In other words, the disjunction is true when at least one of the disjuncts is true. So now let's work backward. When we know that we have a true sentence, in this case, we're assuming that P is the case, P or Q follows. Lastly, let's look at conjunction. Remember what we said earlier about simplification, namely that simplification operates on the truth definition of the conjunction. A conjunction is true when and only when each of the conjuncts is true. So, if we say somewhere in our proof that we have the sentence P, and then somewhere else in our proof we have the sentence Q, we can infer the conjunction of P and Q, or Q and P. Now, I've been talking about these rules as if the order of the premises matters, or at least the language I've used suggests as much. But in fact, the order doesn't matter. Let me explain what I mean by that. So if I go back one slide and I direct your attention to Modus Ponens, you'll notice that the rule form says that in order we have a horseshoe, then we have the affirmation of the left side of horseshoe. In other words, we have the affirmation of the antecedent, and that yields the consequent, or the right side of horseshoe. But let's go back one. Take a look at premises 1 and 2 in our original ed argument. Premise 1 is E. Premise 2 is E horseshoe P. It doesn't matter that premise 2 comes after premise 1. What matters is that premise 2's antecedent, that is, the if part of the sentence, is affirmed already in premise 1. So the Modus Ponens move is legitimate regardless of the order that you see the two premises, the horseshoe and the affirmation of the antecedent. Okay, take another look at these. Maybe jot them down. Make sure you find the chart in your textbook for these rules. There is a chart that will give you all 8 rules. And now let's look at how we can deploy these rules. So what we're doing in this video is ultimately going to be a little bit more complicated than what you'll be asked to do in the exercises on your quiz and in your exam. In other words, notice that the argument is given, and it's not the case, at least in the slide, that the proof is constructed. But remember, as I mentioned earlier, there's lots of practice where the proof is constructed for you in the exercises, and your job is to complete the proof by citing and justifying the line numbers, citing and justifying the step that you've inferred from the relevant line number or numbers and the rule that was employed. So here we have the following argument: P or Q, not P, Q horseshoe S, and our conclusion is S. Now, what I'd like you to notice is the fact that there's only one operator for each of our premises. We have a wedge or disjunction in premise 1. We have a tilde or negation in premise 1 or premise 2, and we have a horseshoe in premise 3. If you go back through your rules, you'll remember that, or you'll be reminded by looking at them, that each of the rules focuses on what happens to dismantle a specific operator, that is the operator that governs the sentence, or what happens in order to assemble an operator. So it doesn't matter how complicated the sentence is. What matters is what operator drives the sentence. So in this case, we've got a fairly easy way of determining what's driving each sentence because there's only one operator. So here is the derivation worked out. Sentence 4 comes from premises 1 and 2, and the rule is disjunctive syllogism. So we have the following. 1, 2, and 4 read like this: P or Q, not P, so Q. Sentence 5 is the conclusion. Once we've derived 4, we're now in a position to use 3 and 4 to derive S, the conclusion. 3 and 4, by Modus Ponens, give us sentence 5. Now, when you're thinking about how you can work the derivation for an argument, you're going to want to think in terms of assembling or disassembling sentences by way of operators. That is, by way of negation, conjunction, disjunction, and horseshoe. You're going to want to think about what the goal is, that is, what the conclusion is, and how the elements, that is, the premises offered, will get you there. Another way to say this is, when you look at the conclusion, you look at the premises, you're going to want to look to see what operators are involved, and then think about which rules employ those operators, or which rules work to assemble or disassemble those operators. All right, so we've covered the basics of natural deduction. There's at least one other video available that focuses on practicing your natural deduction skills. Of course, if you have questions, let me know. Like everything else in critical thinking, the skills that we're working on here are developed by way of lots of practice. So make sure that you set aside time to become familiar with and then skilled at working or enlisting the rules of inference to derive the conclusion of a valid argument.